I'm trying to learn. Typically just
Which one is it in this stack? Yes. That's how.
Okay, folks. Let's go ahead and get started.
If you haven't turned in the lab, turn it in at the end of class so that we can go ahead and get started. The first thing we're going to be doing is we are going to discuss the quantum numbers and the shapes of their orbitals and how it's all interrelated. Then we're going to talk about these orbitals as we start to build up atoms. And as we build up atoms, what we start to see is we start to see nodes within a specific type of orbital. And these nodes are areas where electrons cannot exist. Once we do that, we will then get into electron configurations, and we'll use the information that I ended class with on Tuesday to help build up electron configurations of atoms. We will be dealing with electron configurations today, and I will pick up with electron configurations on Tuesday. Now, I wanted to just give you a heads up. For the next 3 weeks, I am not only going to be lecturing in here on Tuesdays and Thursdays, but our labs are going to be lectures as well. This kind of allows me to go a little bit slower on every single topic and yet still cover the material. And so, again, I'll mention it on Tuesday, but we're actually going to meet as each lab group down in 105 for the next 3 weeks so that you have regular places to sit rather than no backs to chairs like we would have to do in the lab. Any questions before I get started? Okay, so let me show you step number 1. On Tuesday, I introduced quantum numbers. Quantum numbers are a lot like an address for an electron. This idea of the Schrodinger equation that gave us these quantum numbers arose due to the fact that when you have a 2-electron system, there is more going on than just proton-electron attraction. Because when you have a 2-electron system, you not only have proton-electron attraction, but you're going to have electron-electron repulsion as well. So the Schrodinger equation takes that into account. And basically, the Schrodinger equation spits out a set of numbers called quantum numbers that allows us to predict the most likely place of finding an electron, or the most likely address. Now, that first quantum number that I mentioned on Tuesday, and yes, I'm kind of reviewing a little bit of what I said on Tuesday. That first quantum number that I gave you on Tuesday, the principal quantum number N, tells us what shell the electron is in. Is it in the first shell, meaning it's right up against the nucleus? Is it in the second shell, which is a layer out? Third shell, so on and so forth. In other words, it's kind of like an onion, where we keep adding layers onto the onion. And so what we're doing is we're adding these shells onto our atom. And the higher the shell number, the further away from the nucleus the electron resides. And as mentioned, there is a direct relationship between the principal quantum number N, the shell number, and the period on the periodic table. The second quantum number. The second quantum number was the angular momentum quantum number, L. And the angular momentum quantum number L describes the orbital shape. Is it an S subshell, meaning that it's going to be spherical? Is it a P subshell, meaning it's going to have one of these dumbbell-shaped orbitals? Is it a D subshell, which for the most part means it's going to have a cloverleaf-shaped orbital? Or is it an F subshell, meaning it's going to have one of these, which I was unable to draw for you, but I did find a nice picture. So that is your angular momentum quantum number basically describes the shape of the orbital and is called the subshell. Then you have your magnetic quantum number. The magnetic quantum number describes what axis the electron resides on. And those magnetic quantum numbers were related to the principal quantum, the magnetic quantum numbers were related to the angular momentum quantum numbers by the fact that the magnetic quantum number was anything between a negative L and a plus L. So for S, that's 0. There is only one possible orbital in an S subshell. But in a P subshell, there are 3 possible orbitals. There's the -1, the 0, and the 1. And again, this is describing the axis that the electron is most likely on. So, for example, a P subshell that has a -1 magnetic quantum number means it lies on the x-axis. A p subshell, meaning it's dumbbell shaped, but has a 0 for the magnetic quantum number, means that it's going to lie on the z-axis. And a p subshell, meaning it's dumbbell shaped, that has a positive 1 magnetic quantum number, means that it's going to lie on the y-axis. Now, folks, I'm not going to make you memorize whether it's on the x, y, or z axis. Don't worry about that. I'm just trying to illustrate how those numbers generate this idea of where the electron is most likely to reside. And then D we have, so in a D subshell, D means L is equal to 2. So for the magnetic quantum number M sub L, that can be anything from a -2 to a +2. So you're going to have a D that is a -2. You're going to have a D that is a -1, a D that is a 0, a D that is a 1, and a D that is a 2. Again, I don't want you to memorize, oh, this is a cloverleaf on the XY axis, or this is a cloverleaf on the YZ axis. That's not what I'm asking you to know. All I'm asking you to understand is that there are 5 orbitals in the D subshell. And we can, the Schrodinger equation generates these numbers and basically helps us to identify what axis the electron is most likely to reside on. And yes, if you want to take a picture of this diagram, go for it. It's going to be in the notes because I am recording. So it should be available on the Zoom lecture, but just in case you want it for yourself on your phone, you have it. And then M sub S was our 4th quantum number, and basically each of these orbitals, the maximum number of electrons that each orbital can have is 2. So in the D to the -2, the maximum number of electrons is going to be 2. Even though it has 4 lobes, the maximum number of electrons is 2. A +1/2 and a -1/2. In this D sub 0, the maximum number of electrons that it can house is 2. So each of these orbitals can house 2 electrons. And that is the M sub S quantum number. So question. I'm asking you for your questions regarding quantum numbers and the shape of the orbital and what it all means.
I have a question.
Yes.
Will we have to be able to draw the shape of these on the test?
You will not have to draw. I can't draw, so I'm not going to expect you to draw. Plus, when we, let me just, I don't want to use that, but I want to, let me just illustrate how quickly it can get very chaotic. Okay. We said that with n is equal to 1, the only orbital was a 1s. And that was a spherical orbital around the nucleus. That one's easy to draw. we said when n is equal to 2, then you have the option of a 2s and a 2p. The 2s is going to be spherical. Still easy to draw. And up to this point, we could have had 2 electrons in this one and 2 electrons in this one for 4 electrons. Now, the 2p has 3 orbitals. There's my XYZ axis. It has 1 on the y-axis. It has 1 on the z-axis. And it has 1 on the x-axis. If n is equal to 3, then we have a 3s, a 3p, and technically a 3d, though those don't get filled immediately. Here's my 3s. And there's the 3p. You can quickly see why I'm not going to have you drawing. Because it does get very, I can't even put the D in here, to be honest. I don't even know where to start for most of the D's to put them in here. So no, you're not going to have to draw. But I love the question because I kind of drew it so you could at least see the first 5 shells and subshells. I mean, the first 3 shells, 1, 2, and 3, and the first 5 subshells, 1s, 2s, 2p, 3s, 3p. Questions? Okay. Now, another way to draw these, let's just start with the 2s and the 1s, 2s, 3s. So we have our nucleus. Our 1s encompasses everything around that nucleus. The 2s now, when you get to the 2s and the electrons, what you're going to notice is when I drew this, there was an area where I did not put shading. This area right here. is called a node. A node is an area where an electron will not exist. So when I start putting in electrons, I'll have electrons in this blue region here, and I'll have electrons in this red region, but this black region that I have drawn, there will absolutely be no electrons. No electrons can exist in that region. That's a node. Now, there are angular nodes. That are on the axis, and there are radial nodes. And these exist between two of the same type of subshell. The node I drew here would be considered a radial node because it exists between the 1s and the 2s, where we're talking about the exact same subshell. Here's an example with the 1s, 2s, and 3s. If you have a 1s, 2s, and 3s, you're going to, again, the 1s is this blue region around the nucleus, which would be inside of it. You're going to have a node between the 1s and the 2s. And you're going to have a node, if you go to the 3s, you're going to have a node between the 1s and 2s. And you're going to have another node between the 2s and the 3s. Those are all radial nodes. Radial nodes. Because they are nodes that exist between the same type of subshell. You don't get to angular nodes until you get into the P's. You won't have an angular node until you get to a P subshell. So here I have a diagram of the P subshells. How do I know it's a P, by the way? Let's start there. How do I know it's a P? It's dumbbell shape. So the shape is what tells me that it's a P. Now, let's talk about how I recognize what's going on here. Feel like I'm turning in circles. Okay, so the easiest one to see is this one that's on the z-axis. So that's why we're going to focus on it. You will notice this blue and gold dumbbell that's really, really tiny. Well, the first time we get a P is in the second. So that represents the 2P, that little bitty tiny one. That's because the first time we ever see a P is in the second shell. There's not a P in the S, I mean in the 1. The first time you see a P is in the second shell. So that little bitty tiny thing is a 2P. Now, once you get started on the 2Ps, then every shell after that is going to have a P. So this, while this tiny one is a 2P, the next one out is a 3P, and then the next one out is a 4P. So what we're seeing here on the outside, the most outer one, is the 4P. Questions about that, because it's going to be related to something you got to know for the homework. It's also going to be related to something you got to be able to do for the test. Before I get into radial and angular, let's look at a D. Why do I know this is a D first? Because the majority of them are clover shaped. So I know it's a D. Where's the first time we encounter a D? What shell? 3. So that means this innermost one here, this tiniest clover leaf, has to be a 3D. The next one out is the 4D. So again, we're applying some of these quantum mechanics. We know what L is based off of the shape. What the angular momentum quantum number is based off of the shape. We then can figure out what N was, the principal quantum number, based off of where that shape first appears. In the S's, it appeared in 1. So that's why it was 1S, 2S. In the P's, it didn't start until 2. So that's why you would start with the 2P, 3P, 4P, so on. In D's, it doesn't start until 3. So that's why it's 3D, 4D, and so on. Now, there is a way for us to take and determine the angular, the number of angular nodes and the number of radial nodes. We can determine it using the picture. So let me go back to P real quick. Angular nodes appear on an axis. The P subshell has only one angular node because it has only one axis that is separating it. And that's why in between the two lobes on the dumbbell, there is a node. The node is at the nucleus. So the P has only one angular node. Has only one that is on an axis. Now this P has two radial nodes. It has a node that separates the 2P from the 3P. And it has a node that separates the 3P from the 4P. Because radial nodes exist between two of the same type of subshell. 2P, 3P, same subshell. So it's got a radial node in between it. 3P, 4P, same subshell. So it's got a radial node in between it. Looking at our Ds. Now the D has two angular nodes. Again, we're talking about axis. Because of their cloverleaf shape, they have two angular nodes. One along the z-axis in the middle one here, and one along the x-axis. Those are going to be the angular nodes. Now the radial nodes are going to be a node that exists between two of the same type of subshell. We have the 3D and we have the 4D. There is going to be a radial node in between the 3D and the 4D. Now, I know people like things simplified. So how can you do it? How can you determine the number of nodes? Here is a simple set of equations to determine how many of each exist. The number of nodes is going to equal the principal quantum number minus 1. The number of angular nodes is going to equal whatever the angular momentum quantum number is, L. And the number of radial nodes is going to equal the principal quantum number minus 1 minus the angular momentum quantum number, or in other words, it's the number of nodes minus the number of angular nodes. So let's do this in action using this one. Right off the bat, I have determined that this is 2s, correct? This number is going to tell me what n is. And this letter tells me what L is. So my total nodes is equal to n minus 1. So it's equal to 2 minus 1, or in other words, we're talking about one node, total nodes. The angular nodes is equal to L. Now to do this, you have to remember that L of 0 is an S, L of 1 is a P, L of 2 is a D, L of 3 is an F. Because we said that we're dealing with an S, that means that the L is equal to 0. So there are 0 angular nodes. That means for our radial nodes, which is equal to n minus 1 minus L, that's equal to n minus 1 minus 0. So, or I should say, let me rephrase, that's equal to 2 minus 1 minus 0. So that's equal to 1. So there's one radial node, which I actually illustrated. Let's apply this back to the P's. We said P doesn't begin until n equals 2. So this small one is a 2P, the next one is a 3P, the next one is a 4P. So we're dealing with a 4P on the screen. The 4 is your N value. The P represents your L value. So doing our math over here, our total number of nodes is going to equal 4 minus 1, which means there are going to be 3 nodes for the 4P. For the angular, it's all about the L. Well, a P means that L is equal to 1. Therefore, there is 1 angular node, which is what I described earlier. And then the radial nodes, if you want to think of it this way, which makes it easier, there's 3 minus 1, so there's 2 radial nodes, which is what I described earlier. The angular node is the axis. And then the radial node is the difference between the 2P and the 3P. There's one of them. And then the 3P and the 4P, there's a second node. Take a moment and figure out what the 4D nodes are. How many of each there are.
So with the 4D, there's still going to be 3 nodes. The angular nodes is equal to L. Well, when you're talking about a D, and L is equal to 2. So there are 2 angular nodes. One on the x-axis and one on the y-axis. I mean z-axis. And then there is 3 minus 2, or there is 1 radial node. And that is the circle between the 3D and the 4D. Questions? Yes.
We have to memorize the subshells and the L's for the example.
You will need to know this information. Yes, you must know it.
Okay.
There is a homework that is over what we have been just discussing, and if you don't know this, you can't do the homework, and the homework looks a lot like the exam.
Thank you. So when you said that, you know that the radial node is between the third and the subshell, how do you know?
The radial node is always between 2 of the same subshell.
Okay.
So it
Oh,
has
okay,
to be
so-
between a 3D and a 4D.
Yes.
And radial means radius means circle. So that's where it got its name. Other questions? Okay. So this is applying the quantum numbers that we discussed on Tuesday. And I closed out Tuesday with drawing you a periodic table. And basically, when I developed this periodic table, I used the quantum numbers and their relationship to the period number. With this and helium being representative of the NS, where N equals X. And over here, this was the NP, where N equals the X value, meaning it equals the period number. But this area was the N minus one, or the, excuse me, was the, yeah, N, or, X minus one. This is the ND, where N equals X minus one. Now, what I was doing when I developed this periodic table was describing how the electrons are added to an atom of an element. You will always fill up the 1s subshell first. Then you will go to the 2s subshell and fill it up next. Then you go to the 2p subshell and fill it up next. The 3s subshell, then the 3p subshell. Now here's where it gets a little interesting, because if you'll recall, I said when n is equal to 3, we were able to have a 3s, 3p, and a 3d. The question is, why do we skip to the 4s before we come back to the 3d? Why don't we just fill them in the order of the quantum numbers? Why don't we just fill them in this order? Instead of skipping from 3p and going to the 4s before we do the 3p. That is related to energy. On the left-hand side of this diagram, even though it's not shown, is an energy axis. With increasing energy as you go up. Now, if we look at the energy of these shells and subshells, 1s, 1s, 2s, 2s was next, 2p, the 2p was next, the 3s, the 3s was next, the 3p, the 3p was next. But here is where the energy comes into play, because 4s is slightly lower in energy than the 3d. And that is why we fill the 4s before we fill the 3ds. Then we go to the 4p, and then we do the same thing with the 5s to 4d. The 5s is slightly lower in energy than the 4d. That is why you fill the 5s before the 4d. Is because of energy. Now, I'm going to give you two tools to help you memorize how to fill electron configurations. There is this tool, which is probably the best tool to get used to, because you're always given a periodic table on every test. However, another tool Okay. When you use this tool, you can figure out how you fill by going 1S, 2S, then you go 2P, then 3S, then 3P, then 4S, then 3D, then 4P, then 5S, then 4D, then 5P, then 6S, then 4F, then 5D, then 6P, then 7S. And so on. That's the order you fill. The number of electrons in each. 2, 6, 10, 14, and we don't even have any G's or, and so on and so forth, but yeah. Yes.
If you're given the periodic table, how do you know, the number of electrons or like G?
The way you know the number of electrons is it's the same as the number of elements across.
Oh,
So there's 2 elements across for the S, there's 6 elements across for the P, there's 10 elements across for the D, and minus the lanthanide and actinide, there's 14 elements across. It's, you know it the same way, it's just 2 different ways of looking at it. And I'm giving this one because I know a lot of schools, high schools have taught this to help you memorize the energy and the order. But again, it's all in the periodic table. So if you can know your periodic table, you're in better shape. Because again, you're going to get this on the test, not this, but a periodic table on the test. You're not going to get this. You have to know what you're doing there. Questions? Okay, so now I can sit down. I don't have any more diagrams. And we will develop electron configurations. Developing, we're going to come up with two key electron configurations. We're going to come up with the basic or regular or whatever you want to call it. It is being mean. The basic electron configuration illustrates the shell and subshell of every single electron in an atom of an element. We're also going to develop the noble gas configuration. Which is a shorthand notation that shows the electrons in the outermost shell and subshells. Finally, we're going to talk about quantum numbers. Associated with specific electrons. And we're going to do so by developing a box diagram of the electron configuration. The difference between the basic noble gas diagrams compared to the box diagram is that a box diagram illustrates each orbital as a box within a subshell. Now, I will say that with mine, it's not a box, it's actually more of a line, just because I speed things up by doing lines, but you'll also see it as boxes. Now, when we get to the box diagram, what one of the key tools that we're going to be using is a principle that states that you will fill each orbital in a subshell with an electron, with one electron conventional notation for that electron is an up arrow, half arrow really. Before pairing. With the down arrow. Let's start out with, we're going to go ahead and start with carbon. Carbon is atomic number 6. So it has 6 protons. And if it's neutral, it has 6 electrons. It's kind of, what we do next is kind of like that song. Of course, I don't know how many people know The Sound of Music. Let's start at the very beginning. A very good place to start. Let's start at the very beginning of the periodic table with the first shell. We start with the 1, S. And how many electrons? 1, 2. Then we go to the 2s. And how many electrons? 1, 2. And then we go to the 2p. And there, carbon is the second element in the 2p. So 2p2. That is the electron configuration for carbon. That is its basic electron configuration. Now, let's get it to the noble gas configuration. The very first 2 words are noble gas. Where are the noble gases? Group 18 are the noble gases. So it must mean that group 18 plays a role in the noble gas configuration. And what we do is we go, okay, here's carbon. What noble gas came before carbon? Helium. So we put helium in brackets. When we put helium in brackets, we're going, hey, I have everything helium has. I just need to tell you what I have that helium doesn't have. Well, helium, because it is here, does not have the 2s, and it does not have the 2p. So I say, okay, carbon has 2s2 and 2p2 past helium. Now let's do the box diagram. And this is where you got to remember your quantum numbers again. The very first thing I have is an S subshell. How many orbitals does an S subshell have? Picture that pretty little picture I gave you earlier. Kind of looked like a Christmas tree of the orbitals. How many did the S have? One orbital. It was a round ball. So we draw one line to represent one orbital. I ask again, because our next orbital and our next shell and subshell is the 2s. How many orbitals does an S have? One. So I draw one line. Now, think about that picture of the orbitals. How many orbitals were in the P subshell? 3. So I draw 3 lines. Whoops, not 3P, 2P. It's 1357, by the way. Now, let's fill in the electrons. The first one is always spin up. That's just conventional notation, folks. And because we only have one orbital, that means that the next one in this case is going to be spin down. In the case of 2s, the first one is spin up out of conventional notation. And the next one is spin down. Now, when you get to P, you have more than one orbital. If you go back up to here, you fill each orbital in a subshell with one electron before you pair the electrons. So when we start filling in our 2 electrons, the first one is going to go into the first orbital, and the second one is going to go into the second orbital, and both of those go in spin up. That is the box diagram for carbon. Now, for each of these electrons, we can develop the quantum numbers. And you got to memorize, you got to know your rules. So let's go. So let's talk about those rules one more time. The number represents N. The letter represents L. Here's where you got to remember, L equal to 0, it's an S. Or another time you got to memorize this. L equal to 1, it's a P. Don't want to solve. L equal to 2, it's a D. L equal to 3, it's an F. Now, when we were developing this, we said that these lines represent our orbitals. Or in other words, those lines represent M sub L. And the arrows, no. The arrows represent our M sub S. An up arrow means that M sub S is equal to a plus 1/2. A down arrow means that M sub S is equal to a negative 1/2. So really all we got left is the M sub L. And what's the rule for M sub L? It's a negative L to a positive L. So in this case, if S is telling us L is equal to 0, then this means that M sub L is going to be a negative 0 to a plus 0. That means that this is a 0. Same thing with the next one. That is a 0. Now over here, a P means that L is equal to 1. So our M sub L is equal to a negative 1 to a plus 1. So this is a negative 1, 0, 1. Now you have everything to develop all the quantum numbers. But I'm only going to develop a couple of them because of the fact that we're almost out of time. When we develop a set of quantum numbers, we always put them in the order of N, L, M sub L, M sub S. In other words, we're going to read this from bottom to top. So let's just take the two P's and let's create the quantum numbers. The first one is 2, P meaning L is equal to 1. And because it was in the M sub L of a negative 1, and then it's the M sub L is negative 1, and then the M sub S, because it's an up arrow, is a plus 1/2. The next one is 2. The L, because it's a P, means that it's a value of 1. The M sub L, because it is the middle one, is 0. And it's a plus 1/2 because it's been up. Those are the quantum numbers for the 2 electrons in the P subshell in that box diagram. Questions? We will pick up with more of this on Tuesday, where we're going to develop the electron configurations of, on Tuesday, we'll be dealing with electron configurations. We are going to talk about
three of these kinds of electron configurations, and we'll develop more quantum numbers. And then we're going to talk about anomalies because there's a couple of anomalies. So we're mainly going to be doing this on Tuesday. I'll see you Tuesday.
Here's the attendance sheet.
Thank you.